All right, let's dive into it. Picture this. 1926.
1926.
The roaring 20s.
Yeah.
Flapper dresses, jazz music is everywhere.
Yeah.
But something even bigger is happening.
Oh, yeah.
A revolution.
Okay.
Not on the streets.
Right.
But in the world of physics.
It's a time when scientists are realizing that the very building blocks of our universe, atoms, behave in ways that seem utterly bizarre.
Bizarre.
Completely defying the classical laws of physics.
Oh, really?
That had held true for centuries.
Right. It's like everyone suddenly realized the world was playing by a completely different set of rules at the smallest scales.
Yeah.
And right in the thick of it is this guy.
Okay.
Erwin Schrödinger.
Schrödinger, yeah.
Publishing a series of groundbreaking papers.
Groundbreaking.
Today, we're diving into his third paper of 1926.
Third one.
The one where he introduces the world to his famous wave equation.
And what's important to understand is that Schrödinger wasn't working in a vacuum,
right,
so to speak.
Of course.
The world of physics was buzzing with new ideas about quantum mechanics.
Quantum mechanics.
With folks like Heisenberg. And Bohr. Already making waves.
I see what you did there. But seriously, what was so wrong with the old way of looking at atoms?
Well,
why did everything need an overhaul?
The old model.
Yeah.
It imagined electrons like tiny planets orbiting the nucleus sun.
Okay.
It was neat, it was intuitive,
right,
but it had a fatal flaw.
Oh.
He couldn't explain the very specific colors of light that atoms emit and absorb.
Ah, those spectral lines.
Precisely.
Like a fingerprint for each element, right?
These lines were a clear sign that electrons could only exist at certain energy levels within an atom.
Okay.
Not just any old orbit.
So they had to be in very specific places?
Yes.
Okay.
The old model just couldn't reconcile with that.
So Schrödinger comes along.
Schrödinger.
And what does he say? Forget planets, we're thinking about dot waves.
Exactly. His radical idea was this. Instead of thinking about electrons as point-like particles with fixed paths, what if we describe them as probability waves?
Probability waves.
Spread out over space.
Yeah.
Imagine it like this.
Okay, I'm listening.
Think of a radio.
Okay.
Right?
Yeah.
It's not picking up every single frequency out there.
Right.
Just the specific one it's tuned to.
Right.
Similarly, electrons in an atom can't have just any energy.
Right.
Only specific discrete values.
Specific.
They're allowed states.
And those allowed states, those are determined by Schrödinger's equation, right?
Exactly.
This is it.
The equation spits out these special numbers called eigenvalues.
Eigenvalue.
Remember that word? It's the key.
Got it.
These eigenvalues dictate the allowed energy levels for the electron.
Okay.
Just like the tuning knob on a radio dictates which frequencies it can receive.
So it's not about pinpointing exactly where the electron is. It's more like understanding the probability of finding it in certain regions, like a heat map of sorts.
A great way to put it.
Okay.
And that's a huge departure from the deterministic world of classical physics.
Huge.
We're now talking about probabilities, uncertainties. A bit of fuzziness built into the very heart of matter.
And this wave equation, it's not just some abstract mathematical curiosity, right?
Absolutely not.
This thing has real-world implications.
Absolutely. And Schrödinger demonstrates this beautifully in his paper.
Okay.
Even using his equation to tackle a phenomenon known as the Stark effect.
The Stark effect.
Yeah.
Okay, here comes another analogy. I can feel it.
Imagine you have a perfectly tuned guitar string.
Okay, a guitar string.
Producing a single clear note.
All right.
Now, if you bring a magnet close to that vibrating string...
It's going to mess with the vibrations, right?
Yes.
Change the note.
Precisely. And that's similar to what happens with the Stark effect.
Similar.
When you apply an electric field to an atom.
Yeah.
Those neatly defined energy levels, those musical notes of the electron.
The musical notes.
They get slightly shifted and split.
And Schrödinger actually used his wave equation to calculate those shifts and splits.
Exactly.
Talk about elegant.
In fact, he used two methods in his paper. One was a more traditional approach.
Okay.
But the other, that was pure Schrödinger genius.
Okay.
He developed something called perturbation theory.
Perturbation theory.
Yeah.
Sounds a bit ominous.
Nothing to worry about.
Okay.
It's actually quite clever.
All right.
Think of it like this.
Okay.
You're trying to build a tower of blocks.
Right.
Perturbation theory says,
okay,
start with a stable base.
Okay.
Then carefully add one block at a time.
Okay.
adjusting as you go to maintain balance.
So instead of trying to tackle the entire complex system of the atom and the electric field all at once,
Right.
he's breaking it down into smaller, more manageable steps.
Precisely.
Okay.
And this method, it's not just some mathematical trickery.
Right.
It has huge implications.
Huge.
It allows us to apply the power of Schrödinger's equation to more complex, Messier, real-world scenarios.
So he's not just telling us how atoms behave in isolation.
Right.
He's giving us the tools to understand them even in the presence of external forces.
Exactly.
Like electric fields.
Yeah.
But does any of this actually translate to something measurable?
That's where it gets even more fascinating.
Okay.
Schrödinger wasn't just content with describing these energy levels.
Right.
He wanted to connect his theory to what we actually observe.
Okay.
The light emitted by these atoms.
Okay.
Those telltale spectral lines.
So he's going beyond just saying, here's where the energy levels are.
Yeah.
He's figuring out how those energy levels translate into the actual intensities of light we see in those spectral lines.
Exactly. And to do that, he delves into some pretty intense math.
Intense math.
Using matrices to connect the dots between his wave equation and the observable world.
Matrices.
Yeah.
Okay, before everyone's eyes glaze over, can you give us the non-math whiz version of what's going on here?
Imagine a grid.
Okay.
Like a spreadsheet.
Okay.
But instead of numbers tracking finances,
right,
each cell holds information about the likelihood of an electron transitioning between different energy levels.
Okay, I'm starting to get the picture.
Okay.
So brighter spectral lines mean a higher probability of that particular energy transition happening.
You got it.
Okay.
The brilliance of Schrödinger's approach is that he's essentially translating this abstract wave function, which describes the electron state, into something tangible and measurable.
Yeah.
The intensity of light.
It's like he's giving us a decoder ring for the atom. But speaking of honesty, there's a section in his paper where he talks about some discrepancies between his theoretical predictions and the actual experimental results.
Right.
That's a bit unusual, isn't it?
He might seem unusual.
For a scientist to openly acknowledge where his theory falls short.
But that's the hallmark of a true scientist.
Okay.
Schrödinger, being the meticulous physicist he was, realized that some of the predicted intensities didn't quite match up with what experimentalists were observing in the lab.
So he's not trying to sweep any inconsistencies under the rug.
No.
He's putting it all out there.
Exactly.
Saying, hey, this is what works beautifully, and here's where we still have some head scratching to do.
Exactly.
Okay.
In fact, he even goes on to predict that certain intensities should change in predictable ways when subjected to stronger electric fields.
Okay.
Essentially inviting further investigation.
Right.
And that's the beauty of science, isn't it?
Yeah.
It's a constantly evolving process.
You're right.
Building upon the work of others.
Right.
Always pushing the boundaries of what we know.
It's like he's throwing a scientific baton to future generations.
Yeah.
Saying, all right, I've taken it this far, now it's your turn to run with it.
Right.
Which brings us to the legacy of this paper.
Okay.
It wasn't just about explaining the stark fact, was it?
It wasn't.
This was about laying the foundation for something much, much bigger.
Absolutely.
So how did we get from this seemingly abstract equation to, well, everything around us? Our smartphones, computers, all this technology that relies on our understanding of the subatomic world.
It's a fascinating journey.
Okay.
Schrödinger's work sparked an explosion of research in quantum mechanics.
Quantum mechanics.
It led to the development of quantum electrodynamics.
Quantum electrodynamics.
Which explains how light and matter interact.
Right.
And eventually paved the way for our understanding of semiconductors.
And semiconductors, those are the backbone of modern electronics.
Exactly.
Wow.
They're the heart of our computers, our phones, even the very device you're using to listen to this right now.
It's mind-boggling to think that this one paper, published almost a century ago, had such a profound ripple effect on technology.
Yeah.
And, well, modern life as we know it.
It really highlights the power of a single elegant idea to change the world.
Right.
And it underscores something even more fundamental, the importance of curiosity.
Curiosity.
Of constantly asking why.
Why?
And seeking deeper understanding.
Deeper understanding.
Schrödinger's work reminds us that even when faced with seemingly insurmountable challenges, a little bit of creativity and a lot of rigorous thinking can lead to breakthroughs that redefine our world.
So to bring it all back to you, our listener, Why should you care about Schrödinger's wave equation?
Yeah.
It's not just about the history or even about the technology it enabled. It's about appreciating the power of human ingenuity.
Yeah.
To unravel the mysteries of the universe.
It's about recognizing that even the most complex scientific concepts have real-world implications.
Real-world implications.
Often in ways we couldn't possibly imagine at the outset.
And it's a reminder that there's always more to discover. More questions to ask, more layers to peel back in our quest to understand the universe and our place in it.
Exactly.
Which brings us to our final thought.
Okay.
Something to ponder as you go about your day.
Right.
Schrödinger's equation opened up a whole new world at the smallest scales.
Yeah.
But what about the universe at its grandest?
That's a good question.
We now know the universe is expanding,
right.
But what drives that expansion? What is dark energy, this mysterious force that seems to defy gravity?
Big question.
Could it be that somewhere in the quantum realm, hidden within the very principles Schrödinger helped uncover, lies the key to understanding the universe's biggest mysteries?
It's possible.
That's a deep dive for another day, perhaps.
Another day.
Thanks for joining us.